Hello. And yes, more neutron decay cosmology, though this is turning into something larger or different because it works at different scales. But the principle is let's approach it from we'll try both at the same time. Okay, so right now we're looking at a picture. Let's pretend that this is like the primordial thing that exploded into the Big Bang. We'll just call it that, or we'll call that a neutron. Okay, and we'll see why in a moment. Yeah, so there's a neutron or the little Planck ball or whatever that decayed into the universe. Okay, and this is this larger sphere is going to be the cosmological constant, like the minimal density that you can have. And let's create the surface of the universe, which will be in this cardioid shape, and it's just a matter of scaling, really, so let's not get all bent. Right, because what's important here is that we are demonstrating a minimal to maximal density, basically zero-ish to infinity. There we go. With this curve, right? Like if there was a ball here, this is a single cycloid. If there was a ball here, if it would be here, this is minima. It falls down the gravity well. Let's look at the large scale cosmic scale. It falls down the gravity well to an event horizon where your speed is maximal. You're falling straight down. You're falling at c, right? You're only falling at like hardly anything, and then you're falling faster and faster and faster. This is like a path of least action from minima to maxima. Or we could see it's a neutron, and the neutron just decayed. And now this is the electron, and the electron is a field or a fluid flow that goes from minima down to the proton surface, which is this black hole. And this is not scaled appropriately, but we're just looking at gradients and that sort of like a more generalized geometric approach to this structure of the universe, as I suggest. But there's a problem here, right? Because you fall and then you hit the air. So this would be like event horizon, right? Like at the large scale, right? Hydrogen fell to event horizon. Okay, so event horizon there, but what happens to it then? Now in my model, what it would be is like pool, and you fell into it, and so you pop out this side because with the way the energy, like you hit a pool ball, and if you shoot a pool ball and it hits this ball, but if there's a ball over here, which transfers the kinetic energy, so the infalling neutron falls right through this one and reappears here and then falls again, and that's the concept of the neutron decay cosmology thing. And then at the more quantum level, while we're still using gravity, basically, it's like we're using this topology of gravity, this gravitational gradient idea. But what we're going to do is like you fall, and the way we're going to preserve the angular momentum is we're going to create like a spinner thing. Boop. Right? What I like to call Shirley's surface, because I discovered it I discovered it and really explored the weird topology of it. Because the thing is, when you come down on this surface, you're going upright. Let's just pretend you're walking down on the surface, right? You're walking down the surface, you go through there. Now you're on the inside of the blue section, still walking upright, this way. And so this single-sided radially symmetric surface can nicely sort of model CP violation in that, all your orientations got inverted because you went through the puncture point. So it's just has to do with the topology, like a chiral topology or whatever. Actually, it doesn't have to be chiral, but I would do that. I would make the center point inviolate. You can't actually go there. You could only go really close. And then the gradient itself becomes a self-driving heat sink where it's like there's gravity forcing here. So this is very, very dense, a thixotropic fluid. So sheer gravity, because you can keep on falling. You just keep on falling and speeding up and speeding up. So space must be thixotropic. Anyways, and then you fall through the event horizon. You're like coming out. But if you're an electron, this is sort of the half spin thing, right? There's one electron that's on the outside right now, and there's another one that's in there as a positron. And then this one goes to be the electron. This one that was inside is the electron. And the one that was the electron is now the positron on the other side of time. And this is CP violation and accounts for why there is half spin electrons. Like, why do we need two electrons in an orbit? Why? And Dirac found it through the spin inversions. And yeah, but why? Why do we need those both spin inversions? They didn't have to be. If it was like actually a physical fluid and it wasn't a weird topology, it wouldn't, like, that wouldn't happen. But then you'd get spheres and tufts and stuff, which is why spinor topology, so that you can go right through, preserving angular momentum, and you're just going or like divergent here and convergent up there, divergent here, convergent there. But then the convergence basically creates a pressure flow that causes the expansion in this space, which feeds the compression. It's like a beautiful, perfect heat flow cycle. And then, yes, so that is the basic principle. What was there? Oh, yeah, and then what I found cute, was that when you draw just like a single orbit of the surface, and I gotta take away one of these spheres. No, not that one. Boom. There we go. Look at that. Gödel, like life path thing, only paired so that sum 0 at all points, preserving this superfluid nature of the universe. Right, but look at that life path with bounce. But see, the thing is, you'd say bounce, but a neutron is its own anti. So if you watch the flow, the yellow actually becomes the blue. This is the two electrons, right? These are the two spins. Out of phase with each other to fill up the whole space. Pretty. Okay, so that's enough gibberish from me. Have a beautiful day. There's sunlight here. And yeah, let's find out whether this Bledsoe guy was right with his first prediction or what, because I'm game. It's my birthday.